All right, let's go. Ready? Okay. So I'm going over the answer to the teaching example number 2 and showing you guys how we break it down and basically fill in the template. It's exactly the same as what we were doing over here with the first example. And basically what I'm trying to teach you guys is the achieved criteria. So achieved, remember that is color-coded as red. So we are going to be using observations to kind of break down what has happened and to justify it. So I'm just going to make that a little lighter so you guys can see. Good. Better? There we go. Good? Better? Okay. So what we observed is that we had a pale green solution. And that was the iron sulfate. And that was iron 2 sulfate. We mixed it together with a purple solution. And that purple solution was potassium permanganate. And after I mixed those two things together, you would have gotten a pale orange solution. I'm spelling organ. Are we good so far? Pale orange solution. Are we good so far? All right. Let's go through our list and double check what's going on. So if I look up iron 2, I see that iron 2 is a pale green color. And then the sulfate, if I look down on my list, is SO4 2 minus, and that is colorless. So the green color in my solution is coming from the iron 2. Are we okay with that and how I've identified that? Cool. All right, next one here is my potassium permanganate. Potassium isn't on the list because it's very unlikely to be involved in the redox reaction. So I know to eliminate that, that's going to be a spectator. The permanganate, MnO4 minus, is a purple color. So I know that purple is coming from that component of my ionic compound. Are we okay so far? All right. So I'm going to note that as my kind of beginning component. Sorry, let me go through and talk about the orange solution. Actually, no. We'll rather identify what's coming on. So we need to figure out what's going from one to the next item. We know the first one is going to be that permanganate. So we know MnO4 minus is becoming something. And I know that the MnO4 has been involved in this reaction because the purple color has disappeared. So the permanganate is now gone. Do you see my thought process behind that? So I look at my list over here, and the easier way to kind of work through the list is to go from what you have reactants-wise instead of what you have observation-wise. So like, for example, if I was trying to figure out what that pale orange color is, and I was using the list to figure that out, there's actually quite a few things that are an orange color, and so that doesn't really help me. And the risk I then run is if I go based on color, then I might pull up a product that isn't actually going to make sense with the reaction at all. And we'll see that more when we do the iron component. So my permanganate, when I look at that list, there's two options with the manganese. It can either become a solid metallic luster, or it can become an ion that is colorless. It's not the solid metallic luster because I didn't see anything that formed that was a solid metallic luster. So that tells me that the permanganate became Mn2+. And that matches because that is colorless. We good with that so far? All right. The next thing that I'm then noticing is that the pale green solution did change color. So that tells me that the iron 2 must have changed in some form to get rid of that that green color. So I can assume that the iron 2 must be involved in the reaction as well. It's not going to be the SO4 because the SO4 is colorless. And if that reacted, then I would expect my iron 2 to still be there and my solution to still be green. The other thing I can keep in mind is that with SO4, there's lots of different potential options that do have the sulfur. All of them are colorless, and then you have a gas, and we knew there was no gas that was forming. So if I go with the iron 2, I look for the other components that are iron. We have things that are metallic luster. We also have things that are in solution that's a pale orange, and that's my iron 3. So again, I'm using my observations to identify what's going on. I've gone from iron 2 to iron 3 in that case. Do we agree with me on that? Yeah? Okay. So this pale orange color is the result of the iron 3. So now I can go back and I can justify what's going on with my observations. I could also write down that the purple disappears because MnO4 has become Mn2+, and that is colorless. So I'm just trying to state my observations and the reasonings to why that has happened. Are we okay so far with that? So again, I want you guys to use what you have in the reactants. Again, if I had gone through and just picked out things that are orange color, and I said, oh, in this reaction, I must be forming dichromate, which is what this molecule is, or sorry, this ion is, how would I have gotten that from what I have in my reactants? So, or like with the bromine, how would I have gotten bromine out of what I have as my reactants? So don't use the colors as a means to verify your thoughts, but don't use the colors going the other way around to figure out what it is in that sense. Because there's lots of things that are orange, lots of things that are, metallic, brown. So we got to be careful. All right. Next thing I then want you guys to do is state your definitions. So we are going to be stating that the reduction reaction, we have gained electrons. The reduction reaction, we have lost electrons. Okay with that? All right. Now, this is when it's going to get a little bit more complicated because we have to then start integrating in oxidation numbers. When I have a polyatomic ion, I'm going to hold off on that guy and using that for my identification. I'm actually going to use this guy to help figure out what's happening oxidation reduction-wise. I can see here that my charge of my ion is +2, and it's gone up to +3. So thinking about ions, this has lost an electron because the charge is increased. So I would say the oxidation reaction is iron 2 going to iron 3, and the reduction reaction is the permanganate going into the manganese ion. Now, some of you guys are going to be saying to me, but Miss, this is a negative ion and it's going to a positive ion. Isn't that also oxidation? And the answer is no, this is not oxidation. You can only have one oxidation reaction and one reduction reaction. And this is a reduction reaction, but I need to show you how we figure that out. And that's going to be using oxidation numbers. All right. Everything that, and then we're going to fill in the identification of the oxidant reductant. So this is a reduction reaction. This makes this the oxidant, and the reactant in that case is MnO4-. This is the oxidation, makes it a reductant, which is iron 2. Now I've filled it out, and I haven't achieved. We've passed. The trickiest thing is going to be figuring out the pairs and then figuring out which one is which over here. But I will make sure I pick questions where you can figure it out without having to do the merit level stuff. All right, ready to keep going? Teacher, question? You got it? Okay. The next thing that I can then write down for the achieved. So we've justified oxidation and reduction reactions using gain and loss of electrons. You can also justify it using gain or loss of oxidation numbers. Sorry, increase or decrease. So we either justify with gain or loss of electrons, or you can talk about oxidation numbers. So in an oxidation reaction, the oxidation number will increase, whereas in the reduction reaction, the oxidation number will decrease. So again, that gives you another opportunity for the achieve because I'm only looking for one of the two statements. Either you recognize how the oxidation numbers change or you recognize how the electron numbers change. Sorry, the electrons change. We good? All right. So let's now look at the oxidation numbers and how we can justify our answers. I have given you guys the rules for the oxidation numbers, and I decided that this can be a part of the resource sheet because I looked at the clarifications and there's nothing that says I can't put it on there, so I might as well give it to you. I'm testing you on your application of knowledge, not on your memorization, so that was kind of my thought process. These rules help me figure out oxidation number, and then that change in oxidation number can help me then justify if it's oxidation or if it's reduction. So in my first one over here, it's pretty straightforward for my oxidation. You see how we have iron 2, and if I look at the rules, under the second rule, it says elements as monoatomic ions have the same oxidation number equal to the charge of the ion. So whatever the charge of the ion is, that is the oxidation number as well. So since this oxidation number is positive 2, this charge is positive 2, the oxidation number is also positive 2. This guy over here, the charge is positive 3, so the oxidation number is also positive 3. So checking that the oxidation number does increase, and this is now where we get up to the merit level answer we're justifying, will increase. So we're going to go from positive 2 to positive 3. Just be mindful that when we're talking oxidation numbers, the positive sign and the negative sign goes before the number. When we're talking about charge, it goes after. We do that as a chemistry language so we can communicate, are we talking about oxidation number or if we're talking about charge? So that matches what it says up here. Okay? What the other nice thing about this is that the change in oxidation number also tells us the number of electrons gained or lost. So since this change is changed by 1, so we've increased by 1, so that means we have lost 1 electron. So now I'm going in and I'm adding more detail and basically showing you how to take your achieve level answer and bring it up to a merit now. Any questions so far about that? Okay. All right, keep going. Okay. This guy over here, that is now another monoatomic ion, so its oxidation number is also positive 2. So that one's nice and easy. This one here, we're going to have to start combining some of the oxidation number rules to figure out its number. Its number is not -1. So if we look at our rules, this one only applies for monoatomic ions, so ions with only one atom. This guy here has multiple atoms, so we can't use that rule directly. So I'm going to have to start using some other rules to combine them together. I'm going to use this rule over here. Oxygen has an oxidation number of -2. And I'm also going to use this rule over here. Polyatomic ions, the sum of the individual oxidation numbers equals the charge of the ion. So let me show you what that means. So with my, I'm going to get another piece of paper. With my permanganate, what those two rules together mean that I have permanganate, Mn, and I have 4 oxygens, and I'm going to write oxygen as OX, so that way it doesn't look like 40. And those two together make my permanganate, MnO4 minus. When I start plugging in those oxidation numbers, I can actually solve for my unknown, which is my manganese, my unknown. So we're going to change this guy to X. We're going to use the 4, and we're going to multiply it by the oxidation number of oxygen, which I found from this rule over here is -2. And we set it equal to the charge of this polyatomic ion, so we set it equal to -1. I then have X plus -8 equals -7. X equals, add 8 to each side. Sorry, -1. What am I doing? That cancels out. X equals +7. So Mn, in this case, equals positive 7. Do you need me to backtrack? Or are you okay? Just some algebra. So what that tells me is that the oxidation number has gone from positive 7 to positive 2. So that is a decrease, which is what we were saying with reduction. Oxidation number decreases. So it decreased by 5. Sorry about that. So that means that this guy gained 5 electrons. So even though we're looking at this overall charge and we're like, oh, it's -1 to positive 2, we're actually looking at the manatees itself and how it has changed. Yep. All right. So I have a polyatomic ion. The oxidation number of the polyatomic ion is the same as its charge. When I add all the atoms together for their oxidation numbers, it should equal this number here. So manatees is my unknown, so that I treat as an X. That's what I'm trying to solve for. Oxygen, based off of the rules, is -2. And so I'm going to do -2 times 4, because there's 4 oxygen atoms in a permanganate. So I have X plus 4 times 2 equals -1. That's -8 equals -1. I add 8 to each side, so that way the 8 cancels out, and I have X equals positive 7. So the manatees is 7. And that matches what I've said over here, because I see that my oxidation number has decreased, which is a sign of a reduction reaction. Cool. All right. Do be mindful of things, because there are some exceptions to the rules. So if oxygen was in hydrogen peroxide, instead of being -2, it'd be -1. If it's with fluorine, then it's positive 2. So just be mindful. There's some instances where it's not going to follow the normal rule. All right, let's go do the example over here from the last lesson. Do you guys want to give it a go, or do you want me just to walk through it so you have another example? Walk through it? Me? Okay. So hydrogen is the ion. I look at my rules. Ions have, sorry, this is a monatomic ion, because there's only one atom there. So its charge is the same as its oxidation number. I also see over here, hydrogen compounds has the oxidation number of +1. So in both cases, I know that this guy, I'll add the details, oxidation number has decreased. So I'm just adding that kind of note. Our definitions, oxidation number has increased. All right, so I know I've gone from +1, and then I need to figure out what number is it going to. Again, we go to our rules. This is now hydrogen in the elemental form. So I see here, in the elemental form, atoms have an oxidation number of 0. So this is going to go from +1 to 0. So it's decreased by 1. I'm giving the specific numbers of how it decreased. And since I've only had a decrease in 1, I've gained 1 electron. So 1 electron is gained. Cool. All right, next one. You will? Okay. Here's my magnesium. Magnesium in the elemental form. So again, it follows that first rule. Its oxidation number is 0. It's gone to the ion, and that's a monoatomic ion. So it follows rule number 2. The charge is equal to the oxidation number. And again, I see that it's increased, which is good, because that's what I said is oxidation. So it's increased by 2, and we have 2 electrons that were lost. So the trickiest thing is going to be doing that oxidation math. All right, move on. I'm going to give you guys some practice, okay? So I have a worksheet for you guys. Find it. Sliced it in half. Go. There it is. Okay. here is an oxidation number worksheet for you guys to do. I'm going to pass this guy out. Basically, it's asking you to figure out the oxidation number of the different things. In some things, you have polyatomic ions, or you have some molecules, and you just have to be mindful of doing that oxidation math that I talked about for the permanganate. Treat it like an algebraic equation. So keep in mind when you're looking at the formulas, that's 7 oxygen. So you're doing -2 times 7. Also be mindful if your unknown has a number with it as well, because it means you have 2 chromium atoms. So you're going to have to do some division to get the oxidation number for the atom by itself. All right, I'll pass this out for you guys to work on.